up and running now. 1.5 questions. Let's at least try to get a bunch in. One thing we're not short of in this class is questions. That's good. Liz. Yeah. And to take each of these three factors here, 5i square root 3, and I had to take them to the third power. So 5 times 5 times 5 is actually 125. 5 squared is 25, and then when you take 20, you have to multiply it 3 times. Mm-hmm. This should be correct. If you do this 3 times, which is fine, you're going to have 5 times 5 times 5, which is 125. No getting around it. And I times I times I is I cubed. And now let me explain this one. If you take the square root of 3 times the square root of 3, you get 3. But then I have to multiply it by a square root of 3 again. Right? You got to do it the third time. And then it's just a matter of I did 125 times 3 is 375. I cubed is I squared times I. And I know what I squared is. That's just a negative 1. So that's how I came up with. And there shouldn't be any... maybe I could look at your paper after class so we could take a look at it. You should have come out with the same thing, doing it that way. Hopefully that's what they have in the back of the book. Yes. 57. Okay, let's find my way here.
Before you get to explain, can I ask you something?
Yes.
Okay, you got 5i square root of 3.
Yes.
And then for the answer on the side, you got negative 375 square root of 3i.
Yes.
Can I just do it that way and put the I before the square root? Or would you mark it?
The I really should be before the square root. I just said that because it's a little less confusing. So honestly, I didn't write it the best up here. So if you have the I before the square root, that's better. This is the same. See, here's the only problem. If you get a little, you know how it is when we write a lot of math, we don't get real fussy about how long we make the roofs over our square roots. And if I accidentally made my roof too long, it might look like the I is underneath it. That's the only reason why I suggest you put your I's ahead of time. And I should have followed my own advice here. So, yeah, that I in front is very good. Now, 57. Okay, what are we trying to do on this? You're trying to write the quotient in standard form. Okay. Actually, I may have this one. Let me just take a look. Yeah, I do. Okay, here we go. 57. Well, I started with, I believe, what was in the book. Okay, now what I didn't show you is how I squared 4 minus 5i. So I'll tell you what, I'm going to do that on the bottom. There's no detail shown on this, so let me just kind of do this little sidebar down here. Okay, what happens when we square this? Well, you square the first term. That's no problem. Then you square the last term, and you get positive 25i squared, which is minus 25, right? Because I squared is negative 1. And then you take 2 times the product of the two for the inside. Negative 20i, negative 40i. And then what is 16 minus 25? So do you see now where I got that? I'm trying to show you where I got the negative 9 minus 40i. So is everybody with me up to that step? Because if you're not up to me on that step, you won't get what I'm doing next. take the product of the two terms and double it. That's just how you how you multiply out a perfect square. If you don't like that, you could just go ahead and handshake it out, and you'll get the same. Or if you don't like that, or don't remember that. So when what's 4 times negative 5i? Negative 20i. Double, negative 40i. That's where I got that middle term. All right, is everybody with me up to here now? Then I realized I had to get rid of those i's down at the bottom, so I had to do the multiplication by the conjugate, the complex conjugate of the denominator. So I multiplied top and bottom by negative 9 plus 40i. Okay. Now, that should give me the difference of two squares on the bottom, the sum of two squares. And what is 9 squared? That we know is 81. And what is 40 squared? 1600. And 1600 plus 81 is 1681. So that's how I got that. Again, if you can't quite get what I'm doing with that, or remember that when you multiply complex conjugates, you get the sum of two squares, you can just go ahead and handshake it out. It should come out. And then, of course, I have to do it on the top. So I get negative 27i plus 120i squared, which what's 120i squared? Isn't that the same as minus 120? Well, then I just divided it up into two fractions so I'd get it in the standard form. And I might be able to simplify those fractions, but I didn't take the time to do that. Can you divide 3 into 1681? Let's see. 5, 15, 38. No, it doesn't go evenly. Okay, yes. 61. Anybody have a question on this one yet? Okay, this one got a little long, but here we go. Well, here I figured we have an addition of two fractions. I must have a common denominator. So I had to think back to my fraction days. And I had, these two factors, 3 minus 2i, 3 plus 8i. And so I needed what? One of each of those in my LCD. So I was missing in this one, the 3 plus 8i, top and bottom. Here I was missing the 3 minus 2i, top and bottom. And that finally gave me a common denominator. And then on top, I had to do all this. It was 3i plus 8i squared. That's the same as 8 plus 8i squared. And over here, what is it? 6i minus 2i squared. I'm sorry, minus 4i squared. 2 times 2 is still 4. Got it below. Okay. And then a minus 4i squared is the same as plus 4. Okay. So now I just combined my numerator a little bit. 3i plus 6i is 9i. And negative 8 plus 4 is negative 4. So now I'm down to this guy. What am I supposed to do? What's the directions? Directions are probably write it in standard form, yeah. So I then said, all right, let's multiply this out. There's no shortcut here because these are not conjugates. So I just basically had to handshake it out. Here's my multiplication results. And that came out to 25 plus 18i. All right, now I got to get rid of that, so I had to multiply top and bottom by the complex conjugate of the bottom. So multiply by 25 minus 18i. Now this, there's a shortcut for. Complex conjugate should give me the sum of two squares. 25 squared is 625, 18 squared is 324. So my denominator is 949. And then, of course, I had to do this wonderful stuff on the top. And to see the final answer, I have to scroll a bit. A lot of horsing around on that one. Not a very short problem, is it? Yes? You mean right here? I think it was just that the book said put the answer in standard form. Well, in standard form, you can't have just an I on the denominator. You can't have an I. So I had to somehow get that I out of the denominator. Only choice, multiply by conjugate. So that's why. Anybody else on this particular one? Okay, another one on 1-5. Liz? Oh, that's because it started off as a decimal. Yes? I would never have a problem with you converting a decimal into a fraction. That would probably get an immediate smiley face from me if I had a smiley face stamp. So there's a first observation. I think the book's rule, kind of their rule for doing things is this. If it begins with a decimal, it's okay to use decimals. Other than that, my advice to you, if it doesn't begin with a decimal, stay away from them. So the idea here was it's a pretty easy square root, isn't it? It's a little bit tricky though. 0.09 is what squared? Isn't it 0.3? Because what happens when you multiply 0.3 by 0.3? You have to mark off 2 decimals and it becomes 0.09. A little tricky. But if you put that in fraction form, bless your heart. I would be so happy with that. That's good. Yeah, because then you get what? 9 hundredths? And then you can see the square root. Oh, cool. On top, 3. On the bottom, 10. It's actually more visible in fraction form. Yeah. You know, I'm just going to guess. I'm thinking of me. My temptation on this would be to write square root. I mean, I know there's an I there, by the way. I'm not ignoring that. But my square root, I think I might have, if I went too quickly, written 0.03. Do you see the temptation there? Yeah. So actually, it's less tempting with fractions. Good. Yes, maybe our last one. Go ahead. 23? You look like you had a bad experience with 23. I hope it wasn't too bad. It's 23's fault? That could be. Or it might even be mine. All right, here we go. 23. You're supposed to perform the addition or subtraction and write the result in standard form. Okay, the big thing there is simple. How do you subtract a quantity? You have to subtract both things, right? So wouldn't that, after you interpreted it, after you subtract, wouldn't it be 13i minus 14, and then plus 7i? Are you with that? Do you get what I just did? Why is it not minus 7i? Because there's a subtraction sign in front of that parentheses. So that means I have to subtract a negative 7i. And when you subtract a negative 7i, isn't that the same as adding a positive? Okay. Now the rest of it you probably don't need help on. You just combine your i's. 13i plus 7i is 20i. So the answer would be 20 what? Well, in standard form, officially, wouldn't you write negative 14 plus 20i, and then there's your a and there's your b. Yep, I guess so. 71? Okay. Use the quadratic formula, okay? And the problem is 1.0 decimal, not real thrilling, but here we go. 1.4x squared minus 2x minus 10 equals 0. Okay, is it in standard form? Yes, because it's set up equal to 0. So we already know here's my A, here's my B, and there's my C. So using the quadratic formula, I would get x equals minus b square root b squared minus 4 times a times c, all over 2 times a. So are we together so far? Okay. 2 plus minus. All right, I guess I would just hammer this out. First of all, please note, we have a negative times a positive times a negative in this minus 4ac part. That's going to be a positive, right? So does everybody see that this is going to be 4 plus something? Okay. Well, what's 1.4 times 10? 14. And what's 14 times 4? 56? Good. Got rid of the decimal. We still got one on the bottom. So basically, we're down to 2 plus or minus the square root of 60. What can we do with 60? We could at least say, what, 4 times 15? And the square root of 4 is 2. Now, it's hard to say where they ended up with format here, but usually when there's a decimal in the problem, they want you to actually break it down into 2 decimals. So now I would take out my calculator, I'd do this as a positive first, calculate it, write my answer down, comma, and then I'd do the same problem, only this time subtract 2 times the square root of 15 before I divide it. Put that after the comma, put both decimal. And the whole reason you put decimal answers here is because they introduced that decimal there. How do you know that's different? That doesn't necessarily differ. I would get it, I'll bet the decimals come out the same. He said they do. Yeah. Just because they look different, be careful. Don't right away think you messed up. All right, we better. I love the questions, as you know. I gotta get a little bit done today. Here's our lesson for the day. Other types of equations. And I guess it breaks down to what? 4 categories. Polynomial equations, equations involving radicals, equations with fractions or absolute values, and then, of course, they always throw in some application problems. I just copied those headlines from the book. Yeah, there's a lot here. Polynomial equations. You know, I'm not sure I can give you any clue as to why they're called this, but they gave us this problem, 20x cubed minus 125x equals 0, and you're probably thinking, oh my goodness, a cube. Yeah. We really haven't been doing anything with those. This is a chapter on quadratics. But just using a simple, good old factoring technique of taking out the common monomial factor here brings this thing back down to life, so to speak. So I've got 2 factors, and since they are equal to 0, you know that you can set each factor equal to 0. And of course, this one is really nice and easy to solve. And this one over here isn't very hard either. And we wound up with 3 answers. Does it shock you? It shouldn't, because we began with a 3rd degree equation. And you remember, you can get as many answers as up to the degree. So it was possible to get 3 here, and we got 3. One answer is 0, one answer is 2.5, and another answer is negative 2.5. So I guess all a polynomial equation is something that might need a little basic algebra to be done on it before you know what to do. So don't just look at it and go, yeah, cubic. Try to think, okay, is there anything I can do to get this lower? Oh yeah, good old easiest kind of, this particular factoring is the easiest kind we learned. So really turned out to be not a very hard problem. Now, this one is a little bit more of a mystery. You think that was scary? Look at, we got a 6 here. But, you notice that 6 is exactly twice. You know, this power is exactly twice that one. If you're thinking and go, you know what? I'm going to just rewrite this, and I'm going to call x cubed some other letter u. Okay? So just for the minute, let me play my game. I'm going to say u equals x cubed. If I rewrote this, this isn't very hard in u's, is it? Doesn't this just become then u squared plus 3u plus 2 equals 0? Now, I think you would agree with me. Isn't this perfect for this chapter? Good old 2nd degree equation. In fact, it's even factorable. But some of you are probably thinking, oh yeah, but this guy's playing pretend here. U is not the original problem. And you're right. I have to come back to reality after I get my answers. Yes, u is negative 2 and u is negative 1. That's nice. But the problem was looking for x. So when you get down to your u solution, you say, all right, I got to bring this back. So for every u, I'm going to put back my x cubed. I've done that. And then solve for x. Well, I'll take the cube root of both sides. All right, there's one answer. Cube root of negative 2. By the way, are there cube roots of negatives? Yeah. It's the odd roots you can take odd roots of negatives. Okay. And then over here, in place of u, I put my x cubed back in again. And what's the cube root of negative 1? Negative 1. So, I don't know what you would call this. So when you see high powers, ask yourself, is one just a multiple of the other? Like here? Well then if I called x cubed u, then wouldn't this be u squared? And the thing that does is it brings you back into familiar quadratic territory. And this, from here to here, this is pretty easy. It should be, based on the kind of things we've been doing. And then, when you're all done, don't forget, I gotta go back to reality, make the substitution back the other way again. Now, wherever there's a u, I gotta put back an x cubed. Is that legal? Yeah. Does it make it easier? Yeah, it makes it livable. Otherwise, this is like, oh my gosh, what is that? And so it's a nice little, you're going to hear this more than once in this class. We will make these u substitutions occasionally to try to make the problem real manageable. Mm-hmm.
So you could just, is there a way to factor out x cubed for those first two terms?
Well, yeah, but the problem with that is it won't do you any good, because the only way it would do you good is if you could factor all 3 of these. And that because you can't, it doesn't lead you anywhere. Did you get what he asked a good question? He said, well, wait a minute, there's got to be another way to do this. Can't I just factor this thing the way it is and leave it as x? problem is, you can't, because to really and by the way, factoring is exactly what we want to do. I can't factor in x cubed out of all three terms, and therefore I can't factor it. And so you're sitting there and you're stuck. And you're kind of at a dead end. That's why this technique kind of comes to the rescue. It's a good question. I like your thinking on it. Okay, here's another one. Now, again, look at fourth. Wow. But you notice again, this power is just twice that one. Aha. So therefore, couldn't I just say, let's call t squared u? Then isn't this just u squared here, and this is u? And now I look at this and go, well, it's still an ugly creature, but at least it's a quadratic. It's got familiar powers. And couldn't I use the quadratic formula on it? And the answer is, you bet. And so I don't even want to see all this detail, but I did the quadratic formula. Now, remember, when you're all done, and you got your two answers, you are not done. Why not? Because they didn't want u, they wanted t. Okay, so below the wavy line, I kind of did the return to reality thing. And wherever there was a u, I stuck a t squared back in. So right here, u equals -1, that's the same as t squared equals -1. And u equals 1472nd, u equals 736, t squared equals 736. And then solve for t. Now you really got it. So it's almost like this is what? Wow. This problem is like from another planet. All right, I need to go to Earth for a while and do familiar stuff. And then when I get down to the end, then at the end I'll kind of return to outer space and finish it up. It's a weird way to put it, but I hope you see it's what we're doing. We're kind of escaping to a quadratic. Then we're doing the familiar stuff, and then, all right, in the end, I can't ignore that it was a t problem, so always have to do that backward substitution at the end. And it makes an otherwise real major stinker into a pretty normal problem. So moral of the story is when you see high powers, A, do not panic. B, see if a substitution would work. See if one power is just a multiple of the other. And then rewrite it with a substitution. Then stop. I would say, where are we on D? Put a smile in there, because now the problem is really manageable. Now use all your normal quadratic techniques. Keep smiling, and then just substitute back. You can eliminate the smiles from that and shorten it by about 3 steps, but then you're not going to be quite as happy. So, not recommended. Got to have you guys be happy. Okay, next. Another kind of problem is this. I know this talk doesn't make sense anymore, but back in the 60s, it was everybody talked about being radical, dude. Okay, well, here's a radical equation, okay? So, wow, is this rad? Cool. But anyway, I know that talk is about 7,000 years old, but anyway, here we go. We've got a radical inside my equation. Yucky poo. Creates problems. I apologize. How do I get rid of that root? Answer, do a root canal. No. The way to do it is get the root by itself on one side of the problem, and then you can get rid of a root by squaring both sides. So what I did here is I simply added 3 to both sides, and now I have my root all by itself. Now square both sides, and then of course it's really simple. Now you're probably wondering, do I really have to get that 3 on the other side before I square? And the answer is no. But here's the problem. If you leave it like this and square it, What, somebody want to tell me what is the answer to this when you square it? Well, how do you square a binomial? You guys know how to do that. How do you square a plus b? Remember, we've been talking about it today. You square the first term, you square the last term, but then what do you have to do? You have to take 2 times the product of the two and double, you know. So in other words, the first term squared, that's just going to be 5 minus x. Cool. This squared is just 9. But then I got 2 of these products. Minus 6 times the square root of 5 minus x. In other words, I still got the crazy root. You follow? You still got a term with the root in it, and you have not achieved your objective. So this is why I'm advising you, get root by itself, then square both sides. You will thank me for that later, because it saves you a lot of kind of wasted, not wasted, but a lot of extra steps that don't really help. Does that problem make sense? Now, here's the same kind of problem, only it's a little bit messier. And you notice this time, sad face, there are 2 roots. Okay, now I have bad news for you. This one's going to take twice as long to do because we're going to have to square both sides 2 times. Let me show you. My first advice to you is get the roots on opposite sides of the equation. And so my first step, if you look up here, is to add the square root of 6x plus 7 to both sides. So it's gone on the left and it's over on the right now. Now, is there anything you can do to get both roots so they're isolated alone? And the answer is no. There's no, I mean, this is the problem right here, this plus. I can't get rid of that 3. I mean, if I bring it over here, I got a plus or minus sign over here, so. Anyway, so, okay, go ahead and square both sides. Yes?
You lost 17 when you're saying 7. It's supposed to be 17, not 7.
Okay.
So, just your answer.
Actually, this is a plus sign, it's really ugly, so this actually was just a 7.
I know, but we thought you was 17.
Oh, well, I didn't do that one, I did the one with plus 7. If you want to do 17, go ahead. I see, I did claim it was from the book. It really won't affect the problem. I mean, it won't get the same answer right, but I mean, the technique is still okay. So this is supposed to be a plus sign here. Anyway, the point of the problem is get one root on the opposite side, and then square both sides. Okay, squaring 4 gives you 16. What happens when you square a root? Good news, you just get that root without square root sign. Okay. Now, bad news. This is a binomial. One part, second part. So when you square it, you square the first term, you square the last term, but then you got to take 2 times the product of those 2. So instead of 3 times the square root of 6 plus 7 times 3 times plus another 3 times square root of 6x plus 7 gives you 6 times the square root of 6x plus 7. And the bad news is, I did not get rid of the root on that side. See that? There's just no way to. Alright, then I just did a bunch of algebra 1. I'm not going to really go through it. And eventually, I tried getting this root all by itself on the right. And guess what I did when I got it all alone? Or as close as I could, right here. I have to square both sides a second time. So there's just no way around it. I had to do it again. When you square 3, you get 9. When you square that. Now, finally, I got rid of all the roots, all the x's under roots. And what did I come down to? I came down to a quadratic. And now, finally, you know what to do with a quadratic. Right? Stick it in your left ear and churn. No. Use the quadratic formula. Sorry. Making some of you sick. Okay. So let me just let you absorb this a little bit. So did you notice how we had to square both sides twice? And I'm sorry, these just don't become very short problems as a result. What caused it is really this minus sign here. Makes this, you know, no matter what you do, you're going to have to do a squaring twice on this problem. I could maybe do another one and this time actually identify it correctly in the book if you want. But let me know if you have some follow-ups on this. To make myself honest up here, we'll say like number 44. Excuse me. All right, let me just, I'm not seeing hands. You're probably wondering, whoa. Yeah, these are a little bit heavy. Then, on the lighter side, the category equations with fractions or absolute values. You already know, I believe, from your previous algebra work, that when you have an absolute value, don't you always have to break it into two parts? For example, just look at this simple one here. The absolute value of some number x is equal to 2. I know that you know there are two answers that make that work, right? We know that x could be 2, and don't we also know that x could be negative 2, and this is going to work, right? So what does that tell you? Every absolute value basically has two branches to it, the polar opposites in signs. So what do I do with a problem like this then? I say in my head, got to break this into two parts. Step 1, do I have the absolute value by itself? Yes. Then break it into branch 1 and branch 2. Branch 1, just kind of ignore the absolute value signs. And branch 2, change the sign on the non-absolute value side. Instead of 9, negative 9. Solve each part. Two answers, 8 and negative 10 are both correct. Okay, so now, those are easy ones. Let's go on to something, well, I guess I don't. Let's find one in the book that's like this, but a little bit more challenging. How about, let's go, how about we do number 70. How are we doing on time? Yeah. Okay, so this is number 70. The problem in the book says the absolute value of x minus 10 is equal to x squared minus 10x. Okay, is the absolute value isolated on one side of the equation? Yes. Therefore, break it into two branches. Branch 1, ignore the absolute value sign. Branch 2, change the sign on the non-absolute value side. Do you see why I changed both those signs on the right? I just literally changed the sign on the whole side, so that's got to be negative x squared plus 10x. Now, okay, go ahead and do normal algebra on each side, and all the answers should be legit. So, I mean, the rest of this is old stuff. You're going to want to get all what? Should we move all the x stuff to the right? So, if we subtract x from both sides, we would be down to that, right? Now, this is familiar territory. This is just a good old quadratic.
Wouldn't it be plus 10?
Yeah, it would, sure would. And you see this one's, thank you. You see this one is factorable? Isn't it x minus 10, x minus 1? Yeah, negative 10. And then how do you solve this? Set each factor equal to 0. So I already got two answers out of that part. All right. Now, let's not forget about part 2. All right, again, let's send everything to the right. I'll explain to you what I did there. So first of all, I subtracted x from both sides, and I added 10 to both sides, giving me this. Just because I don't like to deal with a negative out here, I multiply both sides of the equation by -1. Of course, this remains unchanged. Now, what do you think? Here we have a quadratic again. Is that factorable? Not looking too good, is it? Or wait, is it? Is it minus 10 plus 1? Yeah, it is. Cool. I want to make sure I did that right. Negative 10x plus 1x is negative 9x. Yeah. Set each factor equal to 0. Okay, now, you notice I got a repeat answer here. In the first part, I had gotten an x equals 10. In the second part, I also got an x equals 10. All right, so it's repetitious. But you notice I came up with a new answer over there. So really, I came up with 3. There are 3 solutions to this. And this one I don't need to circle because I've already got it. So, absolute value problems, kind of recapping from your previous algebra work, you always break them into 2 parts. All right. Well, we got a little bit of everything on the assignment. I don't know if I put anything in here. Let me just see. It doesn't look like I did. Okay, now, it's going to be a little different assignment, so listen carefully here. We'll do the every other odd thing first, but then I want to eliminate where it says in the book graphical analysis, I want to eliminate those parts. So, for example, the 25 through 28 part, we're not going to do that. You see the 53 through 56 part, we're not going to do that. And the 71 through 74, there are 3 of those graphical analysis parts. You can just eliminate those. And then of the remaining problems, do every other odd. Is that, hopefully that's not too confusing. What's that? The assignment? Yeah, step 1, don't do the graphical analysis parts. There are 3 of them in the book. But when those are taken out, do the, what's left, do the every other odd, the 1, 5, 9. So if, like, one of those numbers is 27, you're going to skip that because it's a graphical analysis. If it's an every other odd, but it's in the graphical analysis part, don't do it. Thanks, I hope you have a good one.